Alright, so we are going to continue with where we left off yesterday, which was essentially looking at the problem of how do we systematically go about scheduling a data flow graph. Okay, so we'll start off once again by looking at the original structure of the backward filter, and we are then going to look once again briefly at the as soon as possible scheduling, and then sort of go forward from there. What are the things that we can do? So as before, this is our starting point. Node numbers 1, 2, 3 and 4 correspond to addition operations. 5, 6, 7 and 8 are multiplications, right. Once again I am making the assumption as before that the pipeline latency of an adder is 1 time unit, pipeline latency of a multiplier is equal to 2 time units. And they are pipelined, meaning that on every clock cycle I could, if necessary, introduce a new operation onto each of those hardware modules. In the case of the adder, of course, it's fairly obvious because after all it finishes within one clock cycle, meaning that in the next clock cycle it is free to accept new inputs. In the case of the multiplier, it takes 2 cycles to produce the output, but the assumption is that it's anyway free to accept new inputs on the next second clock cycle, even though it is still working on the first set of data. Alright, so with this what we saw was, we first need to identify those nodes that do not have any input dependencies in the way that the data flow graph has been represented so far, right. And what we found was essentially these points, right, correspond to no input dependencies within the present iteration. So, I mean, it's clear from the way the data flow graph is drawn that node number 5 obviously does depend on the output from node number 1. All that we are saying is it does not depend on what node number 1 produced in this iteration, right, because there is a one sample delay between 1 and 5. Therefore, what 5 is consuming is whatever was produced by one iteration earlier. So, within this iteration at least I can clearly say that 5 does not have any input dependencies, right. The other input to 5 of course is a constant, it does not change, therefore it is not considered a dependency in any case. And with this what we saw was, I can now define the critical path, and it turns out to have a length of 5 time units, okay. And once I have got all of that in place, I can then say, okay, if I wanted to construct a schedule of 5 time units, how do I go about doing this? I can basically put down my different time instance 0, 1, 2, 3 and 4 and list the operation over here. What I see is 5 and 7 can be scheduled right at the start. Their outputs are then consumed by 3, which can therefore execute immediately after that, and since it's an addition it just finishes within one clock cycle. There are dependencies over here. 3 depends on the output of 5 and the output of 7. That's why I am drawing an arrow between in this way. The next thing is the output of 3 is consumed by 1 and the output of 1 is consumed by 2, okay. Now obviously 1 has one more input, which is the external input. I am not drawing that explicitly because it is not one of the operations I need to schedule, that is all, right. And similarly, if we go back to this diagram, what we find is 6 and 8 can also be scheduled at time 0 and take 2 clock cycles to complete. As soon as they are done, 4 can then execute. It has a dependency on the outputs of 6 and 8, okay. And now the output of 4, even though it is ready, is going to be used by operation 2, but operation 2 is also waiting for the output of 1. So even though 4 has generated data, I cannot execute 2. I need to wait until both its inputs are ready, okay, which is why 2 still has to execute only in clock cycle number 4, okay. Now this is essentially the same kind of analysis that you would do in the case of a combinational circuit, right. I mean, if you had multiple paths through a combinational circuit that are converging at a AND gate, for example, you would take the different paths and essentially the AND gate, the starting time of the AND gate, so to say, is considered to be the point when all its inputs are ready and stable, and from that point onwards you add the propagation delay of the AND gate and say after that much delay the output of the AND gate can be considered to be actually stable, right. Of course, in the case of combinational circuits we are not saying that the AND gate starts or stops at any given point in time. We talk in terms of the stability of the inputs because they are combinational gates. Anytime there is a change in the input, the gate will respond, right. But in the case of a combinational circuit, what we say is what is the last time at which one of the inputs could have changed. From there, what is the propagation delay of the gate? That determines the time when the output of that gate can be considered to be stable. Okay. You can think of this in the same way if you would like to, right. So now, as I mentioned yesterday, this is something that's called the as soon as possible schedule for obvious reasons, right. Every operation is scheduled at the earliest possible time instant that it can, subject to the dependencies that it has to satisfy. Okay. If I now try and identify, if I wanted to directly implement this, what are the results that I end up with? This would basically imply, first of all, n is equal to 5, right. I need a 5-phase clock in order to implement all of this because it takes 5 time steps to complete one iteration. Number of multipliers is determined by how many multiplication operations are initiated at any given point in time, the maximum among those, right. Over here essentially what I can see is in time step 1, if I write down over here, number of multipliers that need to be there to start this off, in time steps 1 it is 4, or rather in time step 0 it is 4. In time step 1, what is it? It's actually 0 because I am not initiating any multiplications there, right. The multiplications were already initiated in time step 0, therefore the assumption is that those hardware units are not going away, they are still going to finish their work. But I don't need any extra hardware resources, hardware multipliers in time step 1, okay. So 0 over here and there are no multiplications after that, so it basically becomes 0, 0, 0. What about the number of adders? In time step 0, how many additions am I doing? None. Time step 1, again none. In time step 2, I am going to end up doing how many additions? 2. In time step 3, I do 1, and in time step 4, I do 1. And what I am interested in is the maximum of those values, which basically works out to be 2 in this case and 4 in this case. So the number of multipliers I need is equal to 4 and the number of adders that I need is equal to